Swayam Prabha. Digital India. Educated India.
Hi, welcome to today's lecture. So, I hope you have done your assignments and gone through the multiple choice questions which were uploaded. So, today we will start discussing about data and ways of representing data. So, broadly speaking, there are two components of statistics. One is descriptive statistics, which essentially summarizes, that is to basically convert raw data into some numbers. So, that is what descriptive statistics is about. And the other type of statistics is called inferential statistics. Here we want to develop procedures for finding out or making distinct conclusions from the measures that we have drawn from the sample, from the population. Okay. So, there are, so of course, inferential statistics is the most important thing. So, there are few steps which we need to follow in order to understand what are the steps in inferential statistics, right. So, the very beginning, the first thing is to identify what is your question, right. What is your question and who is your population? Let us say you want to market a soap, then and for teenagers. So, what should be the look and feel of the soap so as to attract teenagers to using that. So, your population is a teenager. The question is basically to make a soap of and identify the essential features of the soap, right. So, now you want to have a process of selecting sample, right. So, it is teenagers, but teenagers from where, what is the proportion of boys versus girls in this sample, right. So, once you have done that, and we had discussed in previous lecture that if your sampling is improper, then you might lead to a completely wrong result. Okay. Once you select the sample, you have to analyze the information, right. You select the sample, you ask the relevant questions in the course of a questionnaire, and you analyze the responses given by boys and girls, right. And based on that, you want to make an inference that you can apply for the whole population of teenagers, and then finally you want to determine the reliability of inference, right. You have come up with pink soap with which is more elliptical in nature or oval in nature is what people would want. So, but you want to test the reliability of this inference. So, these are the steps in inferential statistics. Okay. But before the the prelude to inferential statistics is descriptive statistics, and we want to begin with the descriptive statistics. Okay. So, in descriptive statistics, one of the most important things is a variable, right. What is your variable? Okay. So, variable is a characteristic which varies with time and or different intervals. So, our body temperature can be a variable, right. So, we want to figure out whether someone has fever or not fever, right. So, body temperature is a variable in that case. You want to figure out what is the average height of this population, right. So, then height, similarly weight, so on and so forth. So, this is just an example of data of, let us say, 5 students in a class. So, you have the following categories, in other words, you have the following variables. What is the gender? What is the year in which the student, you have selected the students, 5 students from from the hostel, which year they are, first year, second year, so on and so forth. What are they majoring in, be it maths, be it physics, be it biology, so on and so forth. How many courses have they already done, right. So, a first year student would have probably taken 5 courses already, so that means the second semester of the first year, so on and so forth. Okay. And what is the GPA of that particular student? So, what you see that the nature of the variable differs a lot. Okay. So, in case of gender, it is just a category, right. You either have male or female. In year, you have a number 1, 2, 3, 4. Okay. Major is also categories, right. You have distinct categories, maths, physics, biology, so on and so forth. Number of courses is a variable, but it is a discrete variable, right. You can have only natural numbers which is greater than 0, and in terms of 1, 2, 3 like that. Okay. But CGPA is a fraction, right. It is a number which is depending on what is your a total CGPA, it can vary anywhere between 0 and 10, let us say, okay, but you can have any variable which is between these numbers. So, in other words, my variable can be divided into the 4 categories, right. Your type of data can be qualitative. So, qualitative I mean that is it gender, is for example male or female, or you can have a quantitative variable which is essentially like CGPA, or which which year you are in. So, again which year you are in is a discrete variable, and your CGPA is a continuous variable. Okay. So, there are various types of variables you have to identify depending on the problem. Now, let us say we go back to another plot where you have a grade. So, you have the mid-sem exam is over and you have graded the students, and you want to find out the statistics as to who has gotten what grades. Okay. So, there are 10% in the population which has gotten grade A, 30% in the population grade B, 40% grade C, and 20% grade D. So, you can represent it in a what is very popularly known and used, it is called a pie chart. It is attractive in nature. So, what you clearly see, 40 is C and it has the biggest section of the pie chart. So, the area of this pie chart is proportional to kind of the relative frequency of this number. Okay. But so, pie chart is easy to represent, easy to understand, but it has its share of problems. So, we need to know what are its problems. So, imagine in this case there are only 4 grades. So, there are 4 categories. It is easy to come up with the pie chart. Imagine a situation where there are 25 different categories possible. So, in other words, each of these percentage areas will keep on shrinking and shrinking. So, imagine you have one case which is 1% and the other one which is 41%. So, 41 will of course take a huge chunk of this pie chart, but 1% will barely be visible. So, in other words, it is difficult to represent in pie charts when your volume of data increases such that there are multiple different categories possible. So, you can express this categorical data into also in something, another thing which is widely used is a bar chart. So, same as before, you have the percentage in your y axis and you have the categories A, B, C, D. Okay. So, as before, one of the weaknesses or deficiencies of these bar charts is that if you have too many bars, it looks cluttered. Okay. If you have few bars, there it is easy to represent. Okay. So, this is coming to the few bars, and again the same problem that I mentioned before for pie charts, right. So, you have a value 1 which is 2% and another value which is 40%. How can you represent it in the same bar and still the other person can make sense out of it? The 2% for all practical purposes will look like 0. So, it is nearly impossible, but there is a solution. So, what we do is when the variation in data is huge, as is in this particular plot, you have 3 categories A, B, C, where A value is around 50 and C is maybe even 600, right. So, what you can do is introduce something called a break. Okay. So, you want to show that there is significant difference between A and B. So, you have whatever is the range maximum of C, till there you can have a continuous axis in y, but after that you can introduce what is a break, right. So, let us say this guy is 800. So, you can introduce a break at 400 and then plot again. So, everything still fits into the same thing, but the essential part of the information is there for you to gather, that this is way smaller than this is also part of the information, and this is way smaller than this is also part of the information, and you want to capture both these things in the same plot. So, let us have a simple example. Okay. We are talking about working with quantitative data, right. So, this is the body mass indices of 25 people, right, in a class. Let us say you have this entire of course, these values are continuous variables. So, that you can have all these values. Now, we want to know how can we convert it into a way of representing it. So, identifying categories A, B is perhaps not the good way, because it is not a discrete quantity, but a continuous quantity. But what you can do is you can identify what is the range, right. So, in order to identify the range, we want to know what is the smallest value in this population. So, I can go through this list, and I think the smallest value is 18.3. So, 18.3 is the smallest value, and the largest value is 28.8, 34.2. Okay. So, 34.2 is the largest value, this is smallest, this is largest, right. So, we can divide it. So, 18 to 34 is roughly 18 to 34 is equal to 16. So, we can have a range of 4 baskets. So, we can identify 4 baskets, let us say. Okay. One is 18.3 to 22.3, another is 22.3. So, 22.3 to 26.3. Okay. We can have another one which is 26.3 to 30.3 and 30.3 to 34.3. Now, each of these numbers would mean that you in this basket something will come in if, let us say, that number x is greater than 26.3, greater equal to 26.3, and x is less than 30.3. So, this would make sure the same point x does not go into multiple baskets. Okay. So, this way what we can generate is called a histogram. Okay. So, you convert the data into frequency, you can then plot them as numbers or percentage, and then you can have multiple distributions depending on the nature of the data. Okay. So, your histogram looks something like this. So, you can have these bars. So, in our case we have 4 bars. So, we will have these distribution. So, these are values and this axis is frequency or the number of them. So, it is possible to convert this data. Now, let us say you are going through this exercise, you have this distribution in one case where the total number of observations were 25, and another distribution where n is equal to 600, right. Is it possible to put both of these data on the same plot? Okay. And this is where you have to do what is called as a normalization exercise. So, you know what is n equal to 25 total, and you know each of these values frequencies. So, you convert it, you normalize the curve. In other words, you divide every, if let us say this is my f1, this is my f2, this is my f3, so on and so forth, I convert them into fractions. Okay. So, the nature of the curve will not change. So, this value is now f1 by summation fi. Okay. So, it is equal to f1 by f1 plus f2 plus f3 plus f4. So, this you will get a fraction, it is a fraction. Okay. So, once we have done this, then it is theoretically possible to generate the following plot. I have the same thing, and another one, let us just say hypothetically. So, the way I drew is okay. So, if I were to draw the outlines of this curve would look like this. So, you have one curve like this and the other curve which is like this. So, it is possible to plot both of them at the same time, but you have to do is normalize. But another caveat of this is you must ensure that the data is from a similar distribution. So, of course, there is greater certainty when you have sampled 600 individual measurements, but when you are plotting the same thing with n equal to 25, there is the great possibility that the nature of that distribution will shift. Okay. So, another way of another type of plot which is widely used is called scatter plot. So, scatter plot is just x and y values. Let us say I have x versus y, I have age as one variable and the other variable is let weight, right. So, I can have this generation, age is very let us say 5 years, weight is 10 kgs, so on and so forth, and 50 years age is 60 kgs. So, you have a range. Okay. Now, depending on the nature of this data, you might have points which look like this. So, this is my x, this is my y. So, you might have a data which looks like this, or as I have plotted in this particular curve, you have a kind of a reverse association, where you have greater the increase in x, the y value decreases with a notable exception. Okay. So, this is where your data analysis. So, in this case, do you call it a negative association, or do you want to have a much more nonlinear nature of this curve? So, scatter plots are widely used. So, again here it is better to plot these points as scatter as opposed to connect them, then it is much difficult to make sense out of this data. Okay. But you can make, so if you were to connect it, then you can generate what are typically called as line plots. So, this is an example of a line plot where x and y I have plotted it in a slightly, which looks like S in some way. So, these are reminiscent of bacterial growth curves, but so you can have various functions which describe these line plots. So, it makes sense to connect them with line when you know that the underlying phenomena is actually a physical process which has a given time constant associated with it, or a given mechanism by the way in which it happens. So, there is it's under control, it is not a completely random association. So, that is when you can have very nice linear plots. So, just a small detour on the type of plots. You are all well conversant with linear plots. X equal to y is a very simple plot, and you know how to plot it. You have x, you have y, you take these points, and you take these points. So, let us say this is 1 comma 1, you have minus 1 comma minus 1, 5 comma 5, so on and so forth. You have a line which goes like this, and this is 45 degrees, right. So, in general, if you have a line which kind of shifts up, so in general, why you can have a line which is like this. In this case, okay, so there is an intercept, a non-zero intercept on the y axis, which you can call at y0, and it has a given slope. So, you can have m as the slope, or m is nothing but tan theta. So, in this case, y is equal to y naught plus mx is your equation. Okay. So, so you can have multiple type of functions. So, these are all linear functions that I have drawn. You can have something like this. Let us say this is an example of a parabola. So, this is x, this is y, and y is equal to, let us say, x square, right. So, the far higher you have a non-linear nature of the curve. So, these are, so y is equal to x cubed will look similar, but it have a much sharper peak before x equal to 1 and a lower peak before this. But y is equal to x square is symmetric, but y is equal to x cubed looks like, so y is equal to x cubed looks like this. When x is negative, your y values are negative. Okay. So, these are some of the simple curves. In polynomial, you can have exponential curves which are, let us say, an exponential decay curve will looks like this. Let us say x, this is y. So, if it is y is equal to e to the power minus x, in terms of decay, you have at x equal to 0, you have y equal to 1, and then you have a characteristic time. So, in the most general case, you have x by tau, which represents the time constant of the fall. So, when you are trying to fit data, let us say you have a data which looks like this, then it should immediately occur to you that this has something. It might look like an exponential, it might be it might look like a polynomial. So, polynomials are easy to fit because they have multiple dimensions, but it is not wise to always fit every function with a polynomial. Now, what are the things that you need to keep in mind while doing these plots? Let us go over them one by one. So, of course, when you make a plot, first thing you have to label your variables x and y. You have to put their units ideally. So, let us say this is, if it is age, then I can have years in my, if this is weight, I can have kg. Okay. So, I need to know what are my axes and what are my units. Okay. And I need to choose the appropriate range. Let us say, for example, I want to make a plot of population expansion, right. So, if I plot like this, right, it gives me the impression. So, sorry, this is kg, but let us say it is the weight itself, right, weight which is increasing as a function of years, which will also probably be a linear increase and then some saturation after a point. Okay. So, in this case, if I want to show it is linearly increasing, so let us say this maximum value is around 60. Okay. So, I need to make sure, and I am plotting till 150. So, this portion of my plot is completely destroyed, because I am not using the space. I am visually trying to convey that the weight is not changing much with years, but in reality the weight is changing with years. So, I should actually redraw this plot, that this is from 0 to 60, and my curve should look something like this. Okay. So, if it was like 60, then I can clearly see there is a nonlinear increase initially, which means that initially when kids are growing, their weight increases drastically, but once they reach a certain age, it starts to kind of plateau off. Okay. Again, the other point of breaks, as I said, so in whatever you have done in bar graph, you can have the break here itself. Again, let us say you have a variable x which goes from 0 to 100, and a variable y which goes from 0.1 to 10,000, right. So, here if you put a linear value, so all values which are very small will look like this, just look like a mess here. But what you can do is you can either plot it in log scale. So, if you plot it in log scale, then accordingly every point, so this will be 1, this will be 10, 100, so on and so forth. Okay. So, the points will be well separated out and you can see them. So, it is important to choose appropriate range, and or again as before, let us say this is from 0.1 to 100. What I can do is I can introduce a break. So, let us say I can have 0.1 to 1, and then 80 to 100 if all the data is just here, and then remaining is here. Okay. So, this is how I can really make use of the whole plot and still plot my axis, so that everything is clearly visible. One more thing is, let us just say that you have all your data is here and there is one outlier which is here. Okay. All your data is essentially concentrated in this portion of the curve, but there is one point which is way out, which is an outlier. So, would you bother to plot the entire range, or would you just bother to plot this inside? I think it makes sense to plot the center, then and then bloat it up. Okay. So, you make it big, so then you have all these scatter, and as an inset you can have this higher value where all these points are looking the same. So, make this whole curve as the inset. So, this is called a inset, okay, to handle outliers. Okay. So, now these are some single y plots. Again, let us just say that I have 3 variables, right. Let us say I have 3 variables: time, age, and weight. Okay. 3 variables, okay, and I want to understand, and I want to make a single plot of putting all them together. So, this is where you can make use what is called as a double y plot. Okay. So, you can have 2 axes. So, this is, you can label this as y1 axis, this is as y2 axis, this is x, and you can plot them, let us say, with weight with time might saturate, and age with time has a linear relationship. So, this, if x is my time, this is my weight, and this is my age, then this guy will have a linearly increasing curve. Okay. So, this is just another example of a double y plot. So, in this case I have had a reverse weight in which variable y exhibits a decrease, a linear decrease with x as a function of time, and variable x actually exhibits a saturation profile. So, beyond a certain value of x, it reaches the saturation. Okay. So, now let us solve few examples. So, we have the following example where you have number of visits to a dental clinic in a typical week. So, as you can clearly see, so these numbers are all discrete numbers, you do not have a fraction, because the number of visits is of course a discrete number. But and you want to know what is the best way of plotting it. Okay. So, first you see what is the range, right. So, we have all the way from 1 to 8, and I think when you have this kind of data, it is good to sort it. So, if I were to write the same data together in a sorted form, I have 1. So, the frequency of 1, I can make the frequency of 1. So, I have 1, 2, 3, 4, 5, 6, 7, 8, right. So, and this is my frequency axis. We have the number of visits and the frequency axis. So, for number 1, the frequency is 2, the number 2. So, the frequency of 2 is only 1, right. Frequency of 3 is 1, 2, 3. Frequency of 4 is 1, 2, 3, 4, 5. Frequency of 5 is 1, 2, 3, 4, 5, 6, 7. Frequency of 6 is only 1. Frequency of 7 is 3. 8 is 1, 2. Okay. So, you have the number of visits. Because these numbers are small, there is absolute. So, of course, this axis has to be 1, 2 like that, 3, and because these numbers are small, there is absolutely no necessity to make it into a relative score. You can just have these values. So, for example, for 1 it is 2, for 2 it is 1, for 3 it is 3, for 4 it is 5, okay. 6 it is 1, 7 it is 3, 8 it is 2. Okay. So, you have, if I connect that, actually I should have them as bars. Okay. So, what you see is almost that it is not a unimodal distribution. There is a reasonable amount of variation in the data. So, if this 5 was slightly higher, then you have a nice histogram like shape, but this is different. Okay. So, this is of course a discrete variable, and then you can, I think histogram would be the easiest way to plot it. Okay. So, let us, and histogram is the way to plot it. Let us take another example. So, I have test scores of 20 students, right. I have test scores of 20 students, and I want to know, okay. So, I want to know that what is the average test score, right, as before, and what is the way of plotting it. As before, I think the histogram is the best way of plotting it. Okay. So, we can again go through the same process. We know what is our lowest number, which is around 29, which is our highest number, which is around 93, and we can make it into a histogram. Okay. So, again, where histogram is a good way of representing this. The last one is an example. So, imagine, so the above data is not test of scores of 20 students, but it is test scores of 10 students in 2 exams. So, 10 students, exam 1, exam 2. So, now we have to plot this, so you can make them as 2 separate histograms, but if you want to plot it in the same plot, maybe it is best to put it for each student the x and the y, and that might give us some correlation between how they performed in each of the exams. Okay. So, I guess that brings us to the end of this. Just a brief recap. We discussed the nature of variables, either qualitative or quantitative. We discussed some of the common ways of representation, which is pie chart, bar chart, histograms, line or scatter plot, and then double Y. Okay. So, depending on the nature of the data, the range, the size of the data, you might choose to use the histogram or the scatter plot, as the case may be. When you are trying to look for some correlation, you want to preferably use plots like scatter plot. Okay. With that, I thank you for today's lecture, and I hope that you attempt the questions which we upload for the multiple choice questions. Thank you.